Hey, welcome back. This is 7.1 and we are trying to figure out how to find the area between two curves. Okay, so let's go ahead and start looking at the problem. Okay, so the area between two curves. Okay, you know, what do you know, right? Well, you know how to find the area below curves. So for instance, if you have maybe this curve, let's call it f of x, and you want to know the area from A to B. So this is A, this is B. All you have to do is integrate it, and you'll have the integral from A to B of f of x dx, right? Let's look at another curve. So the same idea, maybe we have this other curve now, and we want to know the area from A to B. Let's call this g of x. To get the area underneath this, we just integrate from A to B of g of x. Okay. So again, what are we doing? We're trying to figure out the area between these two curves. So for instance, f of x and g of x, right? So maybe we have f of x and g of x drawn in the same picture, and we're trying to figure out the area from A to B. In other words, the area between the two curves. How is that going to work? Well, I think you can kind of see how that's going to work if you just subtracted these two, right? So you take f of x, that area, subtract away the area underneath g of x, you end up with the area between the two curves. Okay, so you could literally just take the two integrals and kind of subtract them. F of x dx from A to B minus the integral of g of x dx from A to B. And what you end up with, we could put it in one integral, f of x minus g of x dx from A to B. And that's pretty much it. Okay. With regards to the theory, it's not too much different than what you did with the development of the Riemann sum and the Riemann integral. So you could, you'll have two kind of curves, f of x and g of x. Let's say the one on the bottom is g of x. What you're going to do is kind of cut it up into a bunch of little rectangles. Okay. And then, of course, sum up the areas of these little rectangles, and then take the limit as the number of rectangles goes to infinity, or if you'd rather, as the partitions go to 0, right? So that was all chapter 5, we learned that method. It's the same deal here, it's just now these rectangles, the areas of these rectangles are found by differences, right? So if we have this particular rectangle located at position x sub I, and its width, we'll say, is just some generic change in x, we could get an approximation for the area just by summing up these a sub i's, where the a sub i's will be differences between we want to put the f of x first. Okay. So it would be the sum of the differences of f of x sub I minus g of x sub I, delta x. And then if we take the limit of this thing as the number of rectangles goes to infinity, or as the partitions go to 0, I'll just say the number of rectangles. You basically end up with the integral that we just kind of developed above by taking the difference of these areas. So anyways, you'll end up with the integral of f of x minus g of x dx. Of course, there's some issues with respect to continuity that we kind of have to take into consideration for it to always work. So we'll say this method of subtracting the two curves, the two curves inside the integral works so long as f and g are continuous on whatever interval you're working on, let's say from A to B, and we need to be conscious of what curve is kind of on the bottom and which curve is on the top. So in our discussion, we're saying that g of x is less than or equal to f of x on the same interval. Okay, so we kind of have these small technicalities that we have to deal with as we go through the problems. Usually I kind of think of it as top minus bottom, and we're going to be looking at different orientations, but if you see the picture with my little rectangles, what I do is kind of draw this guy, the Riemann man, and he sort of runs across, and while he's running across, he'll collect all of the rectangles in this bag. And, you know, that's the orientation here. I got to put his mask on him. The orientation is going to be the top curve is the f of x. And you think of it like you're the Riemann man. The top, you know, is f of x, and the bottom is g of x. So top minus bottom curve is kind of how you think of it, where the orientation of the Riemann man is he's running across, collecting up the areas as if he's standing there. Because we're going to talk about other orientations here, so that will become an issue. Okay, so anyways, let's look at an example of this kind of problem. So example, y equals x squared plus 2, y equals negative x, x equals 0, and x equals 1. So we want to find the area enclosed by these curves. The curve y equals x squared is just a parabola with its vertex at 0, 0. If you go plus 2, it'll just shift that parabola up by 2. So our new vertex will be at 0, 2. Okay. And then, of course, we'll have still these points on it. So let's try to draw it. Y equals negative x is a diagonal going downwards. So we can kind of plot some points and get a picture. Okay. X equals 0 is the y-axis, so I'll put that in red. And then x equals 1 is a vertical line going through x equals 1. And it seems our region that we're looking for the area of is this bluish shaded region. Okay, so I can use integrals to do that, and it will just be, again, the integral of the top minus bottom. The top curve in this orientation, if we do our Riemann man, the top curve is going to be the parabola, and then the bottom curve is going to be the diagonal. Okay, so it'll end up being x squared plus 2 minus negative x inside of our integral dx, and it looks like the Riemann man is going from 0 to 1 on the x-axis. Okay, and then it's just integral, integral, integral. So this will be x squared plus x plus 2 dx. And then integrating, I have x cubed over 3 plus x squared over 2 plus 2x. And then this is a definite integral, so I have to remind myself to integrate the thing, evaluate the thing from 0 to 1. So first plugging in 1 into the antiderivative. 1 squared is 1, so 1 over 3. 1 cubed is also 1. And then plus 2 times 1 is 2. Minus, plug 0 into all of that. You'll just get 0 plus 0 plus 0, which of course is 0. Find some common denominators. What do we have? 2, 6 plus 3, 6 plus 12, 6. And that will equal 15, 16, 17, 6. Okay. Okay. Finding the area then, so in this case, they sort of gave you the limit on the limits on the integral, the 0 and the 1, but in general they probably won't, and they just want you to use the places where the curves intersect. So all it is basically you have one extra step. So the area between intersecting curves. What do you have to do for this? Well, you have to find the intersection points for the limits of the integral. So for A and B, we must find intersection points. And in order to find intersection points, what do you have to do? Well, you just have to basically set the equations equal to each other. So hopefully you have some familiarity with that. But if not, let's take a look at an example, right? So second example, we'll say f of x is 2 minus x squared, and then g of x, which is plain old x. So our picture, 2 minus x squared, so that's a parabola, and then it's rotated about the x-axis, and then it's shifted up 2. Okay, so 1, 2. Has intercepts where 2 minus x squared equals 0, so at root 2 and negative root 2, so in there somewhere. Here's the vertex, and it would look like this. So kind of like this. Okay. G of x equaling x is diagonal through the origin, so kind of get a couple points to help us draw this thing. And then we want to know the value of the area, or the area between the two curves, right? Again, maybe think about the orientation. The Newman man is going to be dealing with. Here, the top curve is 2 minus x squared, the bottom is x. So we have our integral, sort of, right? So the top curve, again, 2 minus x squared minus the bottom curve, which is just x. The only problem is figuring out the limits on your integral, the a and the b. So what I'm saying is in order to find a and b, you have to find the intersection points. In order to find the intersection points, you set the two equations equal to each other and solve. So this will be a quadratic. You want to set it equal to 0. So add the x squared to the other side. Subtract 2 on both sides. Factor it. And then you get your two solutions. One at -2 and the other at 1. So it looks like the limits are going from -2 to 1. And then all we have to do is integrate it and we'll have our answer. So it's going to be 2x minus x cubed over 3 minus x squared over 2, and then evaluate from -2 to 1. So we'll have 2 minus 1/3 minus 1/2 minus, and then plug -2 into there. So you get -4, and this will end up being plus 8/3. This will end up being minus 4/2, which is 2. Okay, so I have a find some, do I need common denominators? Yeah. So it's be 12, 6 minus 2, 6 minus 3, 6 plus 4. Let's combine these two though, right? So -4 minus 2 is -6. -6 is +6. Then minus 8/3 with a common denominator of 16. 6. So -5, 6, and -4, 6 is apparently -9, 6 plus 6. This is the hardest part, just doing some arithmetic. -3/2 plus 12/2 is 9/2. Okay. So that would be the area between the two curves. Let's do one that's a little more complicated. think it used to be example 4 in the book, I'm not sure anymore. F of x is 3x cubed minus x squared minus 10x, and then g of x is negative x squared plus 2x. So, the picture is kind of given in the book. I could go through how to plot them, but I think just for the interest of time, I'll go ahead and just give you the picture. So the cubic is going to have intersections where, well, you just set it equal to 0 if you really need to. So for f of x, you know, plug it to 0, 3x cubed, x squared minus 10x, factor out the x, 3x squared minus x minus 10, factor again, so it looks like 3x, probably 2 and 5, right? 5, 2 with the bigger guy negative, positive, so x is 0, x is negative 5/3, and x is 2. Okay, so 2, 3, so 0, negative 5/3 is a little less than negative 6/3, right? So it's about right here. And then x equals 2 is about right here. Cubic, and it's coming in from negative infinity because the leading coefficient is positive. And then it's going to cut through because of the multiplicity. If you don't remember all that stuff, that's all pre-calc stuff. And that's going to zip up something like that. The other guy, g of x, you know, 0 is negative x squared plus 2x. You can factor out negative x minus 2. So 0 and 2, we kind of have those. It's going to look something like this. Okay. Then I need the intercepts for my so what we're looking for is the area between the curves, this area and then also this area. Okay. So in order to pull this off with the Riemann man running in this direction, you note that in the first case the top curve is the cubic and the bottom curve is the quadratic, and then it changes. So you need 2 integrals for the regions. You need a first integral and then a second integral. Okay. So the first integral, the top curve again is just the cubic, the 3x cubed minus x squared minus 10x, and then minus the parabola, which was negative x squared plus 2x dx. And then the second integral will be, the top curve is the quadratic, right? So now it's going to be negative x squared plus 2x, and then the bottom curve minus the cubic, 3x cubed minus x squared minus 10x dx. Okay. For our integrals, we need to know the x values of the intercepts. So in order to pull that off, I need to set the 2 formulas equal to each other. So I need to go, you know, the 3x cubed minus x squared minus 10x equals negative x squared plus 2x, and then solve. Okay, so moving the negative x squared to the other side, the x squares will cancel. Then minus 2x on both sides, you get minus 12x equals 0. Factor out 3x, you end up with x squared minus 12. Oh, oops, x squared minus 4. Factoring again, 3x times x minus 2 times x plus 2 is 0. So my zeros are my intercepts, in this case 0, 2, and negative 2. Okay. So the first one must be negative 2 to 0, and then the second one will be 0 to 2. Okay, so then it's just a matter of solving the integrals. or evaluating them. You definitely want to simplify first. Okay? So you distribute the negative and add like terms. You'll end up with 3x cubed minus 12x for the first integral. And then the second integral, when you distribute the negatives and combine like terms, you get, let's see, negative 3x cubed. It's just the opposite signs, plus 12x dx. And then negative 2 to the 0, 0 to 2. Okay, then you integrate. So 3x to the 4th over 4 minus 12x squared over 2 is the same as 6x squared, negative 2 to the 0, plus pretty much the same thing but with reverse signs. So negative 3x to the 4th over 4 plus then the 6x squared from 0 to 2. And then you're just left with evaluation. So plugging in 0 into the antiderivative first, you'll get 0 minus 0, which is 0, minus, then you plug in negative 2. Negative 2 to the 4th is going to be 2 times 4, 8, 16, minus 6 times negative 4, negative 2 squared is just 4. And then plus, now I'm going to put in positive 2, so it'll be negative 3/4 times 16. And then plus 6 times positive 2 squared is 4. And minus, plug 0 into that thing, you just end up with 0. Okay. Let's simplify now. You're going to distribute a negative. 4 goes into 16 4 times, so it's going to end up being negative 12. Plus 24 minus, again, this will be negative 12, and then plus 24. So negative 12 minus 12 is negative 24, plus 24 is 0, plus another 24 will just give you 24 for your answer. Okay. Okay. So these are all kind of the examples of horizontally oriented scenarios. What we want to look at are kind of sending the Riemann man up the pole, so to speak. So before then, just in these above examples, the Riemann man is kind of going in this direction, right? So he's picking up all of these rectangles that are oriented vertically. Okay. And so his bag, so if this is g of x and this is f of x, the particular a sub I is located at x sub I with width of change in x. The a sub I formula would just be g, I need f of x first, so sorry. F of x sub I minus g of x sub I times change in x. Right? Now, what I was saying is you want to run them off the flagpole. So what do you mean by that, Dave? Well, you're going to have now this sort of orientation where these curves are given in terms of y. So let's call this bottom curve, so to speak, h of y, and then the kind of top curve, g of y. And we're going now, instead of from A to B, like before we went from A to B, now we're going to go from, let's call it C to D. And the Riemann man is oriented like this. Okay, he's running up the flagpole, so to speak. And so now the top curve is the top curve is the G, right? The G of y sub I. So if we were to go through that same process, instead of x sub I, we have y sub I. Instead of change in x, we have change in y. Then there'll be little rectangles in here. We'll just draw one of them. The area formula for that thing, a sub I, is going to be g of y sub I minus h of y sub I times change in y. Okay? And then when we do our limit as the number of rectangles goes to infinity, our formula in terms of y will be just g of y minus h of y dy from c to d. Okay, just as before, when we did our little limit process, we ended up with the integral of f of x minus g of x dx from a to b. Okay. So what's important, in my opinion, is just kind of the orientation, making sure your Riemann-Mann is set properly so that you can identify the top curve and the bottom curve. Right. So there's just these two orientations. A little weird because you think maybe the Riemann-Mann should potentially be on the other side and then running up the flagpole, like maybe he should be over here or something, you know, like I'm doing in red. That's wrong. This is, no. He's on the other side and he's flying up. So if I did the red one, it would seem like the H is the top curve, the G is the bottom curve, which is not right. Okay, so you have to orient him in the appropriate place. Let's put a little mask on him just to make sure he's healthy and safe. Okay, there you go, buddy. All right. So let's take a look at an example of this and kind of go through the why would I bother doing this. And it'll come down to the fact that these g of y and h of y aren't traditional functions, right? They don't pass they're not one-to-one. Is that the deal? Yeah, they're not one-to-one. They don't pass the vertical line test. So they are functions of y, but they won't be functions of x. For some reason, I'm confusing myself. I'm just gonna let's look at the example. Okay. So example 5. So that gives x equals 3 minus y squared, and then x equals y plus 1. I'm going to plot them, and I can kind of think of the orientation and everything. So the Riemann-Mann is kind of, just butchered his legs there. It's kind of going in this direction. That's the orientation you want to think. So the 3 minus y squared, you can kind of think of it as y equals 3 minus x squared, right? So you have a rotation about the x-axis and then a move up 3. But in this orientation, what does that look like? Well, it means the vertex is right here in the positive direction of the x-axis, and then it's going to have a root 3 intercept. Okay, so it's going to look like this. And you compare and contrast that to y equals 3 minus x squared. You know? So y equals 3 minus x squared is this thing. So it's not like you're just, it's not exactly a 90-degree rotation in this direction. It's more of a rotation and a flip. And you don't see the flip because in this case, the thing is symmetric, but you would kind of see it if you were trying to draw. I think you would see it if you're kind of trying to get the reflection, the rotation of this. So instead of having y equals, this would be y equals square root of x. If you wanted x equals square root of y, it wouldn't be like this. Okay, it wouldn't just be a 90-degree rotation. It's a rotation and then kind of a flip. So what you would really have for that would be this guy right here. This would be x equals square root y because of the orientation. Okay, hopefully that makes some sense. So this part of it isn't true. It's this curve. Okay. So anyways, let's get back to reality. We want also x equals y plus 1. So its intercept is at x equals 1, and then it's increasing slope in the direction of orientation, right? So again, the Riemann-Mann is going up the pole here in this direction. So that's the direction the line has to be increasing in slope, right? So it'll have to go up like this. And you could also do some point plotting if you want to. again, with doing a 90-degree rotation, again, it's not a 90-degree rotation, it's a 90-degree rotation, and then a flip about the x-axis. So if you wanted to, it's y plus 1 is right here. If you do a 90-degree rotation, you kind of get, what the heck would you get? You would get something like, this would go here, you get this, but then you have to do a rotation, which would end up right here. Okay, but hopefully this. Okay. So, anyways, what are we after? We're after the area between these two curves. So, the top curve and the bottom curve. What are they? The top curve is going to be the parabola 3 minus y squared. And the bottom curve is the line y plus 1. Okay. We need to know the intersection points in order to get the limits on my integral. So it's a quadratic formula, so y squared plus y minus 2 is 0, so it equals 0. Factor it, you get y minus, it's like plus 2, and then y minus 1. 0, so the limits will be -2 and 1. So you're going to go from -2 to 1, and evaluating it is not so bad. So I'll end up with, I have to distribute. So 3 end up being -1 is 2 minus y squared dy. And then that would be 2y minus y squared over 2 minus y cubed over 3. And then I have to evaluate from -2 to 1. So plugging in 1, we get 2 minus 1/2 minus 1/3 minus, plug in -2, so I got -4 minus 4/2, which is 2, minus -8/3, which would be plus 8/3. Okay. And then we have some basic arithmetic. So this will be finding common denominators. 6/3 minus 3, 6. What am I? Sorry. So it's 12/6 minus 3/6 minus 2/6 plus 4, 5, 6, 6 minus 16/6. So -4, 5, 6, 7, 8, 9, 6 minus 9/6, which is 6 minus 3/2, which is 12/2, minus 3/2, which ends up being 9/2 again. Okay, so that's the idea. How could you do it with x in terms of the other orientation? Yeah, you can, but you don't want to do so. Do not. Kind of do, this is like a do not example, just for people who are curious. How would you do it in the other way? So we have 1, 2, 3, 2, 1, 2, and our graph. And x minus 1. And then let's say we want to do it in the standard orientation because it's fun. The issue becomes that you're not dealing with functions in the standard sense. Okay, so if you were to solve these for y, you would have y squared equals 3 minus x. Take the square root on both sides, and here's the issue: you get a plus or minus root 3 minus x. The linear part is easy. The x equals y plus 1, right? So you just get y equals x minus 1. The problem is you have 3 different curves you're dealing with. Plus 3 square root 3 minus x is like this blue portion of the parabola. Okay, so that would be square root of 3 minus x. And then the bottom curve here is negative square root 3 minus x. This line here is the x minus 1. Right, y equals x minus 1. So the issue, is that this bottom and top kind of issue. And there's two sort of regions then you'll have to worry about, region 1 and region 2. And region 1, the top curve is the line x minus 1. So maybe I should just put y equals x minus 1. And then the bottom curve is the y equals negative square root 3 minus x. And then you have region 2, which means you need two integrals to pull this off, which is more than what most people are willing to kind of do. The top curve in this case is the y equals square root 3 minus x. And then the bottom curve would be y equals negative square root 3 minus x. So it's this curve that this parabola, sideways parabola, isn't going to be kind of a traditional function. It has two pieces in it. You have to take it apart so it becomes a function. Two functions, right? Let's just set up the integral and see how nasty it is. So for the first integral, we have x minus 1 minus negative square root 3 minus x dx. And then we have this other integral, which will be square root 3 minus x minus negative square root 3 minus x dx. We need the bounds on our integrals. So the first integral, set the equations equal to each other, right? So 3 minus y squared, whoops, that isn't it. We have to go negative square root 3 minus x equals y plus 1. Square both sides, you get 3 minus x equals, whoops, not y plus 1, but I need the x minus 1. You need to put it in the x minus 1 form. So you get x squared minus 2x plus 1. It's quadratic, so you get x squared minus x minus 2 is 0. So you get x minus 2x plus 1 equals 0. So the intersects are at 2 and negative 1. So it's going to go from negative 1 to 2 for the first integral, and the second integral will go from 2, and it looks like to the top of the vertex, which should be at 3. So look at that integral versus this integral, right? The moral of this story is that you want to change the orientation when it reduces kind of the number of integrals you're dealing with. So instead of having two regions to deal with, if you do this other orientation where he's kind of running up the flagpole, you just have the simpler integral. Okay, so make that one your quiz. So this is the quiz problem for this section. So you just have to find the area between it. So it's basically just, recopy all this part. Just want to make sure everybody has this kind of technique embedded in their brain somewhere. Okay, so let me write that in my notes. I forget. Okay, let's look at a trig version of these problems. So we're given two functions. F of x is 2 sine x, and then g of x is tan x. And then they kind of tell you the limits on your integral. We want to go from negative pi over 3 to pi over 3. Okay, so a picture is in order. Tan has asymptotes whenever cosine is 0. In other words, at negative pi over 2 and then pi over 2. So tan looks like this. And then 2 sine x is just a sine curve with amplitude of 2. And at pi over 2, sine goes to 1. So, or sorry, it goes to 2 because the amplitude's kind of changed. So what is that going to look like? It's going to look like this. Okay, and then likewise in the other direction. Okay. Pi over 3 is inside of pi over 2, so it's pi about right here. I have to make sure that this, you suspect the intersection point is really at pi over 3, but you're not entirely sure, and you have to make sure there's no weirdness of what's on top and what's on the bottom. If you think about the orientation for one of these wedges, in the first quadrant, the 2 sine is on top and the tan is on the bottom. But if it turns out that we need to go beyond the intersection point, you're going to have another integral to deal with. So you need to kind of find the intersection points and make sure it truly is pi over 3. So just remember, sine is the same as, or tan is the same as sine over cosine. So we can multiply both sides by reciprocal, and you're looking for where 2 cosine x equals 1. In other words, cosine x equals 1/2. And of course, in the first quadrant of the unit circle, the reference angle there is pi over 3. So that turns out to be the intersection point where they hit each other. Okay. There's symmetry involved here, so we need not worry about integrating from negative pi over 3 to the pi over 3. We just start at 0 and go over the pi over 3. But if you do that, you have to multiply it by 2, right? Because if you don't, you're just going to get this first region. To multiply it by 2, that means we're going to be kind of also then getting this other region. Okay, so the top curve in the first quadrant is the 2 sine x. And then the bottom curve in the first quadrant would be tan x. And then we just have a trig integral to kind of evaluate here. So what do we have? 2 times the antiderivative here is 2 negative 2 cosine x minus ln absolute value of secant x, which I have memorized. You may have to kind of think about it. And then we have to evaluate from 0 to pi over 3. And I want to distribute that 2 into the antiderivative before I evaluate. Otherwise, it's just going to be kind of annoying. So my antiderivative, negative 4 cosine x minus ln absolute value of secant x. Whoops, I lost my 2. Evaluated from 0 to pi over 3. So first plugging in pi over 3. Of course, cosine of pi over 3 is 0. Oh, sorry, is 1/2. So you have negative 4 times 1/2. Then, because secant is just 1 over cosine, the secant of pi over 3 will be 2. And then we're plugging in 0. I sort of ran out of room. So it's negative 4 cosine of 0 minus 2 ln of secant of 0. Cosine of 0 is 1, secant of 0 is also 1. So we're getting negative 4 times 1 minus 2 ln absolute value of 1. Of course, absolute value of 1 is just 1. And then we have negative 2 minus 2 ln 2 plus 4. Ln of 1 is 0. I'll just give you 2 minus 2 ln 2. Okay. And then that would be your answer. Okay, so let's call it quits for there, and we'll see you in the next video. Thank you for watching as usual.